So in the last few, like one third of the course, uh, we basically developed some of the probabilistic tools that we need to analyze many problems in statistical learning. Right. So henceforth we'll start looking at specific problems in learning and try to analyze them in a more deeper way. All right, so we'll start with supervised learning, the most basic learning framework. Again, like learning theory is very vast, and we will not be able to cover everything that is out there. We'll just be able to scratch the surface. But still, I'll try to give a flavor of what is there and what kind of tools can be used to study supervised learning. Now, how many of you have already taken a course in machine learning or are currently taking a course on machine learning? Any course on machine learning? Okay, great. So you know what is supervised learning, what I mean by classification, regression, and so on. Right. So I won't spend too much time in defining what, I mean, we'll formally define some of the learning problems, but I'll assume that you're at least at a high level, you're familiar with what these problems are. Now, in most other learning theory or machine learning courses, perhaps the focus would be more on designing algorithms. Right? You're given a particular learning task, and you start with a particular learning algorithm, such as gradient descent or even empirical risk minimization, without perhaps spending too much time as to why you use that particular framework for developing the algorithm. In this course, what we'll basically do is see why it makes sense to look at these algorithms. But at the same time, we'll also spend a lot of time in trying to understand what are the fundamental limits to a learning problem. All right. So suppose that you had infinite amount of computational resources. Then what is the best that you can possibly do? All right. Now, why is this important? Why do we want to understand the fundamental limits, and why not just go ahead and develop algorithms? Well, firstly, learning what the fundamental limits to a problem are has multiple advantages. One is, suppose you know that it is impossible to, for whatever, in the parameter regime that you're working in, perhaps it is impossible to design an algorithm itself. Then really there's no point in trying to design an algorithm, efficient or not. All right. So you know that it's impossible to do anything. Right. So that's what I'll denote. So you have the space of all learning problems. I've not really defined what a learning problem is, but at a high level you understand what this is. So let me just say the learning problem. Right? When I say learning problem, it could perhaps refer to, we can take something very specific like classification, and what are the resources that you have? Maybe the number of data samples that are available. Right? That's one way of parameterizing the learning problem. All right. So now, given an infinite amount of computational resources, suppose that you find out that you are able to somehow prove that it is impossible to design a learning algorithm that achieves the performance that you desire. Then it means that you can't improve things by improving the algorithm. The only way you can improve performance is perhaps by getting more data. Right? So understanding the fundamental limits also tells you how much data would you need to achieve at least a certain level of performance that you desire. All right. But so within this parameter regime, maybe there's another region over here that corresponds to problems that can be solved. Right? So when I say problems that can be solved, maybe this is the regime where the number of samples, maybe the number of data points, is enough to achieve the desired level of accuracy. Right? So you're somehow able to prove that if you have these many samples, then it is possible to design a learning algorithm. It doesn't tell you what is a good learning algorithm or what is an efficient way of designing a learning algorithm, but somehow we are able to prove that if you have these many samples, then it is possible to achieve a desired level of error. Right? But this doesn't automatically tell you whether the computational resources that you have is enough to solve this particular learning problem, whether it's possible to design a good classifier that can be implemented in, let's say, polynomial time, and you can achieve the desired level of error. Right? So in general, in many learning problems, there is another region in between, which is the problems that can be solved efficiently. So much of our course will be in trying to distinguish between these two regions. What problems can be solved? Like, what is a parameter regime where if you're given an unlimited amount of computational resources, you can actually achieve the desired level of performance. All right. But learning theory in itself also tries to understand this particular regime. What problems can be solved efficiently? Although this is a much harder problem. All right. So our focus will be on trying to find out what problems can be solved in the, let's say, given the number of samples, or let's say if there's a noise level in a problem, then if given this particular noise level, is it possible to achieve a desired level of accuracy or not? Right? More of this will become clear as we go along. All right. So let's start off with what is the difference between computation versus learning. Right? To first understand what we mean by learning, what is really the difference between computation and learning? In a learning problem, typically the ground truth is unknown. Right? So there's some variable x. So what you're given is some x, and the goal is to find some y that is related to x. Right? In computation, you know the exact functional relationship between x and y, so then it becomes a matter of whether you can compute the function y, whether you can compute y from x or not. On the other hand, in a learning problem, the relationship between x and y itself is unknown. And the goal is to really understand what is or try to learn the relationship between x and y, whatever this may be. All right. There's also a conceptual difference, although it's a little more, it's not so well defined. There's also a difference between inference and learning. All right, but this distinction between inference and learning is not so clear. It's a bit hazy. What sometimes people make a hard distinguishing factor between inference and learning, but sometimes it's not so much. So typically the difference between statistical inference and statistical learning is that the data generating distribution is unknown. Right? So let's think about a problem where you want to infer the relationship between x and y. All right, the exact relationship between x and y is unknown. In a learning problem, typically you don't know anything about the distribution of x or the distribution of y or the conditional distribution of y given x. In an inference problem, typically you know something about these data generating distributions. You may not have full information, but typically you have at least some partial information, perhaps what is the distribution that generates x, or the joint distribution between x and y. All right. But in a learning problem, typically you're only given data samples drawn according to the ground truth distribution and nothing more. Okay. At any point, if you have any questions, please feel free to stop me. So this was all very high level stuff. So let's go down to some specifics. Right? So what is a supervised learning problem? A supervised learning problem is one where So supervised learning problem is one where, again, you're given some data that is labeled. For instance, it could be, let's say, a bunch of images which are labeled whether they have a car in them or not. Right? And the goal is to design a learning algorithm that, given any image, you should be able to say the classifier should be able to say whether this particular image has a car in it or not. Right? And the goal is to design an algorithm that captures the relationship between the, let's say, image and the labels. Yeah.
When we say computation versus learning,
Okay.
the problem is to identify unknown ground truth, right? Like what exactly we meant when we are referring to ground truth.
So when I say ground truth, it is, let's say, the relationship between x and y. Again, I'm being very loose over here. I'll make things more precise in just like 2 minutes. Okay. All right. So one can consider different examples, right? So before we proceed, let me just set up some notation. So typically, we're given, let's say, a symbol that I'll denote X, which I'll call an instance. So for example, if we are talking about object detection in images, then X corresponds to the image and Y corresponds to the labels. So the Y could be 0 if there is no car in this, or it could be a 1 if it has a car. But yeah,
Mostly looking at the classification.
for the classification problem, right? In the specific example of the classification problem, X would correspond to the image and Y would correspond to the class to which this image belongs. This is of course assuming it's a binary classification problem, right? But in general, you could consider something more arbitrary. So let's say a topic modeling, you're given a document and you want to understand what topic does this document belong to. Is it a document that is about physics? Is it about chemistry? Is it about linguistics and so on? All right. So once again, X would correspond to the document and Y would correspond to the label, which is the topic that is associated with this particular document. All right. So this X would be the document and Y would correspond to the topic. Right. But at the same time, let's also try to set up what set this X and Y can belong to. Right. So in a topic modeling problem, let's say X could come from the space of all possible documents. How would you model the space of all possible documents?
It's like all documents, the name of the title or the body content.
Correct. Let's not worry about the name or title, right? We were worried about the content. How would you model? So let's suppose that you've just come in and somebody has given you the problem of designing an algorithm for finding out the topic corresponding to each document, right? And you want to set this up in a mathematical framework.
In mathematical framework, we need a way to represent the documents in the form of some
Correct.
mathematical, which we can apply our mathematics. So
Correct.
mostly we have to represent them as a vector. So
Great, okay.
Since for most of the learning algorithms, we can't have a variable size vector.
So let's not worry about, again, at this point, let's not worry about the most efficient representation, but we want a representation that captures all possible inputs that our learning algorithm must take.
With some class of functions.
Okay, let's not worry about functions or the relationship between the document and the topic. My first point is to understand what set does this belong to.
Finite.
Yeah, but what is the alphabet?
Vectors. Maybe some subset of
Unicode.
document.
Okay, great. So this is one thing. Let's say every document can be represented using, let's say, Unicode characters or ASCII characters, whatever, right? So one way to represent a document is,
One,
I'm sorry?
one word.
Again, I'm not worried about the specific representation, right? I want to find out what is the set to which this document belongs to. So we need to make some assumptions, right? We could perhaps start with, well, maybe the document is always going to be in English, right? So in that case, X would correspond to so you have A to Z, maybe capital letters, numbers, and some special characters. So it could be, let's say, an ASCII document, or this could be, let's say, whatever, Unicode, or some particular format. Right? Before you even design a learning algorithm, the first step is to understand what kind of inputs are you going to get to your learning algorithm. Right? And in general, unless you make some prior assumptions on the documents, this could be so strings from this particular alphabet of any arbitrary length. Right? So if I take this to be some set A, then the domain set, that is the set from which X can come from, is the set of all possible strings of elements from A, the set A. Again, to set up some more notation, just a little bit of a recap. So whenever I say X underline, it means that this is going to be a vector, and hopefully the length of the vector will be understood. If I want to distinguish between vectors of different lengths, then X superscript n and X superscript m will denote vectors of length n and m respectively. And I'll use lowercase typically to denote deterministic vectors or deterministic symbols, and uppercase to denote random vectors. Right? If I have a set, so typically this calligraphic X will represent some set. A, B, X will represent sets, and A n, B n, X n will be the set of all n tuples of elements taken from the respective set. And A star, if the length is not necessarily finite, then this will be union n equal to 0 to infinity A. Right? Set of all possible strings of all possible lengths with elements taken from the set A. Right? This is some basic notation that we'll use throughout the course. Okay, so that's one way of determining what could be the inputs in a topic modeling problem. Let's now consider an object detection problem in images. Right? Now once again, what could X be? So this could be, let's say, image of, let's say, a particular size. An A cross B image, right? So again, what is X?
Set of 1 to 56 cross the same trace.
The set from?
1 to 256.
Okay.
Cross X cross X.
Sure. So basically, you could model this as a matrix. If you're looking at, let's say, black and white images or grayscale images, then you could represent this as, let's say, 0 to 255, as is more standard, to the A cross B. Right? So all possible matrices with entries coming from 0 to 255. Or if this is supposed to be a color image, then in general X could be 0 to 255. If this is an RGB image, then this could be represented as a tensor 3 by A by B tensor, each corresponding to one particular channel. Right? And what is Y? The label set could be 0, 1 if it's a binary classification problem, but in general you could have multiple classes as well. Right? Similarly, for a spam classification, suppose you want to design a spam classifier. This could be, let's say, an email. And the goal is to classify each email as being either spam or not spam. And again, for this as well, you could use the same. You could use the same set as inputs, and the label is either 0 or 1. Suppose you are given a speech, let's say a recording of a speech or some sound recording, and you want to identify the speaker present in this particular recording. How would you model the input?
C power n.
Yeah?
C power n.
C power n y.
So the signals are basically complex.
Y complex specifically? Are you assuming something about?
Feature extraction. There will be some, you will import the input and then.
Correct, but what kind of inputs are you assuming? Yeah?
Waveforms.
Okay, so waveforms would be coming from what domain?
Real.
So real would be standard. I think perhaps you referred to complex because generally these are transformed to a Fourier domain or such. Right? But in general, yeah, you could assume that this is, say you have a waveform, let's say a set of all functions. I'll use right. In general, this could be a waveform of, let's say, duration capital T with, so it can be any arbitrary function from 0 to t to r. Right? Or if this is a sampled signal, then this would be r to the m, where m is the number of samples that you've taken from in the interval, let's say 0 to capital T. Right? That's one way of modeling the input. Question?
So I think the speech should be finite then.
Which?
The speech recognition. The
Correct.
Speech is always finite.
It is a finite length. That's what we're assuming for now. Again, on the depending on the specific problem that you have, all of this would change, right? This is just one example. And y, the set of labels, could correspond to the number of speakers that you have. Speaker 1, speaker 2, and so on. Right? Assuming that you have a finite number of speakers among which you want to distinguish. Okay, another problem could be, let's say, forecasting the price of something like oil or some stock. Right? Again, it depends. Maybe you have historical accounts of what the oil prices are. You could have something else as well, some other data. So again, a way of modeling this is, let's say you have historical price, maybe for m days. So one way of modeling this is so. But perhaps you may also have some additional information, right? Maybe some other information about, let's say, geopolitical situation or the price of something else, let's say gold. And maybe you want to understand how these two are correlated with each other. So all of this would have to be captured by this kind of inputs that you want to take in. Right? And the output is some real number which corresponds to the price for, I don't know, tomorrow or next month. Okay. Great. So what we've now kind of established is that the kind of supervised learning problems that we will consider, we assume that there is an instance which is drawn from a domain set, and corresponding to this instance there is some label which we'll call the true label, right? And that's drawn from some particular label set. before we even try to set up or design a learning algorithm, we have to know what is the domain set and what is the label set. That's a minimum requirement. But we'll make pretty much no additional assumption beyond this particular point. Okay? Anything extra is something that comes at a premium. All right? But this is a bare minimum. You cannot proceed without knowing what the domain set is and what the label set is. And another point that I'd like to make is that generally we'll assume that this label set is fixed. Right? It's maybe the set of reals or either some finite set. Okay? So typically we will be considering problems like classification and regression. There are a whole bunch of other learning problems which will not be captured in this particular framework. Okay? But at least for the first part of this course, this is all that we will focus on. In fact, we'll spend much of our time purely talking about binary classification. And then we'll see how these ideas can be extended to multi-class classification as well as regression. Okay. Great. So now we also, in addition, so this information is given to us, but we also need a mathematical model for the data generation process. We don't know what the true model is, but still we need a conceptual model that we can work with. Right? So we'll assume that there is some x and y, and we want to know the relationship between x and y. We're always given x, and the goal is to predict y. Right? So what is the relationship between x and y? One particular model is the following. Let's assume that x is a random variable that is drawn according to some unknown distribution px. Okay. Now again, another word about notation. I'd use px to denote the distribution of x, irrespective of whether x is a continuous random variable or a discrete random variable. It should be understood from the context. All right. So x is drawn according to some px which is unknown. Now, to complete the generation model, I need to tell you how y is related to x. This tells you how x is going to be generated, but it doesn't tell you how y is going to be generated given x. So one way is to say that there is some function, unknown function, g from x to y, which is again unknown. So given x, y is a deterministic function of x. All right? And maybe g is drawn from some class of functions c. All right? And this c will be given a special name. It's what I call a concept class. Yeah?
Y could also be drawn from conditional distribution.
It could. I'll get to that in a moment. Right? This is one particular model. All right? And it's going to be a special case of the next model that I will consider. But this is conceptually the easiest to understand. That's why we'll treat it as a nice special case before we move to the more general setting. So G is drawn from some concept class where the C may or may not be unknown, may or may not be known. It's a very general setup. For example, C could be the set of all functions from x to y. All right? Or it could be some subset of the set of all functions from x to y. Great. So that's model 1. Model 2 is again x comma y, which is slightly more general. These are jointly distributed according to some joint distribution pxy. Again, this is assumed to be unknown. All right, and this is what I'll refer to as the agnostic setting. So conceptually, why should there be some additional randomness in y given x? It could be because you don't observe everything that is required to learn y. For example, let's say if we go to the problem of example of oil price forecasting, maybe the historical price of oil is not enough to determine what the price of oil should be tomorrow. Right? It could depend on a whole bunch of other factors which you don't have access to. So there's an additional source of randomness that you don't have access to, and that is why given x, y is still a random variable, which is distributed according to some py given x. Right? Or it could be the case that you know everything that has to be that there is to know about y given x, in which case y is a deterministic function of x. Right? For example, if you take, let's say, an image and you want to know whether there is a car in it or not, if you take the space of all possible images, then you should be able to determine whether that has a car in it or not. Right? Or if it belongs to some specific class of cars, let's say. All right? So it's more reasonable to model the object classification problem in using model 1, but let's say forecasting the price of oil would most naturally belong to model 2. But in any case, model 1 is just a special case of model 2, because py given x is just a deterministic relationship. Yeah.
Is it possible that x comma y cannot belong to any joint? You can't. There is not. There does not exist any joint distribution from where x y comes.
This is going to be our assumption. Right? We will always assume that x and y are going to be drawn according to some particular joint distribution, which is fixed but unknown.
Is it true for all real problems?
Okay. So we'll make a. It's in general it need not be true, but it's a reasonable assumption to make for most problems. All right. So the important assumption is that pxy is fixed and does not change as we design the learning algorithm. All right, so in particular, pxy does not change with time. We assume that it is fixed. Right? For example, let's say the object classification problem, at least the relationship between x and y does not change with time. Because what you classify as being a car in an image or not does not change with time in any way. But something subtle to note is that the input distribution could potentially change with time or some other way, depending on how you gather this particular data. Maybe the training set was gathered in one particular way, but as you deploy it in practice, the distribution could be different. Right? Which means that there is now a mismatch or there is some change in the data distribution or some change in the ground truth. We will assume that there is no such change. All right? We'll assume that everything is fixed. Yeah.
If I'm designing the X, Y is fixed, but after we have designed a learning algorithm and we have deployed it,
Correct.
there might be data drifting and all that.
True.
So are we assuming that there is no?
We are assuming in this course, we will assume that there is no data drift. All right. That's fundamental. All right. We will also make another assumption. Okay, let me. All right, so what does it mean to design a learning algorithm? Again, what we want to do is develop, or we want to design an algorithm that will predict y given x. But based on what? So we assume that we are given some samples, some labeled samples. So we're given n labeled samples, which we assume are all independent and identically distributed, and they come from the same distribution as Pxy. So Pxy in the agnostic setting, or if I'm going by model 1, where there's a fixed concept class, we assume that the function g is fixed, and each xi is IID drawn according to Px. That is going to be the assumption.
Is there any specific case to choose IID?
That's the simplest to work with. And in many cases, again, it's reasonable to assume that they are IID. All right? So again, this is, when I say this is for the purpose of this particular course, right? But there have been a lot of works to even study the case where these xi's are not IID. Sometimes this may not be a reasonable assumption, because perhaps because of your data collection process, it could be that x1, x2, x3 are not independent and identically distributed, but x2 depends somehow on the value of x1 that you got, and so on and so forth. So all of that can be modeled, but for now we'll assume that it's an IID process. Okay. So this is what I call the training set. And I'll denote this S. Okay, so S will always denote my training set. Remember that this training set is it's a random set. The number of samples is again going to be fixed. We'll fix n, and each data point xi, yi is going to be distributed IID according to Pxy. That's the fundamental assumption. So what is a learning algorithm? So a learning algorithm takes this training set as input and outputs some function h, all right, which is your predictor. All right, and we'll assume that h is taken from some allowable class of functions, which I'll call the hypothesis class. So some examples of H, for example, if you take this to be, let's say, a linear classifier, if you're trying to design a linear classifier, then script H essentially corresponds to all possible linear classifiers. Right? Assuming that, let's say that I have a linear classification problem or a binary classification problem.
What's the difference between a hypothesis class and concept class?
The concept class is one where the ground truth is coming from. All right. The hypothesis class is what the learner is going to use. For example, maybe the relationship between x and y is something that is non-linear, but you are going to design a linear classifier or a linear regressor. So then the concept class could potentially be the space of all possible functions. But your hypothesis class is only going to be the set of all linear functions.
Why do we even define a concept class? Because it's anyways only one function is chosen from that.
Correct, but sometimes you may know what the concept class is. That's additional information.
Yes.
All right. So in general, the hypothesis class could be different from the concept class because in general you don't know the concept class. But we'll also look at special cases where you know the concept class and you take the hypothesis class to be equal to the concept class.
Is it possible that you also take your hypothesis class to be different from the concept?
Yes, in general, we're going to assume that the hypothesis class is going to be different from the concept class.
So hypothesis class has to be superset.
Not necessarily. So it could be very different. There could be no intersection between the concept class and the hypothesis class at all. Because in general, you don't know, right? You don't know what the concept class is. But typically, the hypothesis class is chosen based on a number of requirements, for example, computational complexity. And we'll see later why you would want to choose a hypothesis class in a certain way. Now, at the face of it, it may seem like I should choose my hypothesis class to be as rich as possible so that it contains the concept class and everything else. So the natural first choice would be just choose the hypothesis class to be the set of all possible functions from x to y. All right? It's a natural assumption to make. But as we'll go forward, we'll see that it's a very bad assumption to make. That's a horrible choice to make. So in the example of the binary classification problem, we could consider linear classifiers. So in the binary classification problem, I need to specify what x is. Maybe x is r to the d, and y is either 0 or 1. There are only two possible classes. Maybe the linear classifiers are the set of all h, which is perhaps can be written as the sign of some A transpose X minus B RD and B in R. Yeah.
Can I say my small h is a function?
So small h is a function.
So we define as a small g, which is mapping from
X to Y.
x to y.
Yep, right.
But what about my h? What is mapping to map?
So h is also mapping X to Y, right?
Right.
So this.
We defined a data set as an input, right?
So, yeah, so let me just. So h is a mapping from x to y. All right. So this is a predictor. So any predictor takes as input x, one particular x, and outputs one particular y. All right. That's one predictor. The learning algorithm takes the data set and outputs a predictor. All right. So maybe it might be clear if you're already used to machine learning algorithms, then perhaps you want to look at, let's say, neural network classifiers. All right. So in a neural network classifier, again, let's assume the same binary classification problem. Maybe this is the set of all the H essentially would correspond to the architecture of the neural network, or the model, or the hyperparameters, and so on. Right? So this could be the number of layers, number of neurons in each layer, so all of this would essentially determine H.
Can't we say H is set of all functions because neural network can approximate any function?
So there's a difference between approximation and taking this to be the set of all possible functions. So ideally, what you want to be able to do is approximate all possible functions, but we'll see why it's not a good idea to just take the set of all possible functions. There is going to be a very clear distinction between these two. All right? Okay, so H essentially corresponds to the architecture of the neural network. And what do I mean by a learning algorithm? You could think of the learning algorithm as the process of training a neural network to give you a good classifier. All right? Remember, the learning algorithm takes the data set as input and outputs one particular classifier. The predictor is the final result. It's one particular realization of the neural network with one particular set of weights. Okay, does that make sense? Fine. Yeah, so it's also important to note that in general, the hypothesis class is not equal to the concept class. Yeah.
When we say concept class is set of all functions in which
No, it may not.
it's a set of functions.
A set of all it's a set of functions from which the ground truth is drawn.
So can we say among those functions in the concept class, there exists a function in which it can map exactly to x to y?
Correct.
So other functions are belongs to problems can be solved that we talked earlier or efficiently can be solved.
Which one?
So hypothesis.
So hypothesis class is chosen by you. You get to choose the hypothesis class. So there's two steps. So given the learning problem, your first step is to choose a hypothesis class. And then the second step is to design the learning algorithm. All right? And we're going to decouple these two problems. All right? First, we'll fix the hypothesis class and try to understand, for this hypothesis class, can I design a learning algorithm that does what I want, what I expect it to do? Okay? And then we'll see what makes a hypothesis class good. Okay? Questions?
So is it right to discuss about hypothesis or concept class in the data generation model of rho x1?
Correct. So basically, the concept class would determine the class of pxy's that the data is generated from.
When we say concept class, there should be a function that maps x exactly from X to Y, right?
Yes.
So, but when we discuss this concept class in the model 2,
Correct.
where X comma
So
Y
in
is
model 2, there is no notion of a concept
Concept
class, right? Because when I say concept class, it refers to a deterministic relationship from X to Y. In general, model 2 subsumes model 1, right? Where Y is could potentially have an additional source of randomness. If there is no additional source of randomness, then I'll assume that the relationship from X to Y comes from a concept class. As I said, the concept class could also be the set of all possible functions from X to Y.
even if we take a concept like a set of all functions from X to Y,
Yes.
then also we can't, means there won't be any function, because when we say X comma Y is sampled from row X Y, there is no deterministic function from X to Y, right?
So that depends on Pxy, right? So when I say model 1, I'm restricting the class of Pxy's.
No, when we say model 2, X comma Y.
When it is coming from model 2, then there's no notion of a concept class at all, because there is no, in general, there is no deterministic relationship from X to Y.
So even if we take set of all functions, that won't be.
It is not enough to describe the data generation process. Yes. So if xy comes from model 2, then no deterministic model can capture the relationship from X to Y. All right? But when I'm assuming that I'm operating in model 2, it includes deterministic functions and random functions from X to Y. All right? So model 2 is a strict superset of model 1. Okay? If I can solve model 2, then I can solve model 1, but the reverse is not true. Okay? And that point will become important as we go along. Okay. All right. To just give some intuition as to how one must choose H, or how H can play a role in designing a good learning algorithm. So choice of H. Right? So ideally we would want to choose a H if we are operating, let's say, in the completely agnostic setting, then we would want to choose H to be rich enough. Right? Because we want to capture all possible relationships from X to Y. Because we don't have any additional information about the actual relationship between X and Y. Right? But at the same time, what we'll explore in the first part of the course is that H should not be too complex. All right? And why so? Because if H is, in a sense, too complex, then maybe you need too many data points to learn H. All right? And this is most accurately captured in the following way. Let's suppose that the actual relationship between X and Y is something very simple. Okay? But let's say I have 2 points, or let's say I have 3 points. I have only 3 data points. Let's assume that X equal to Y equal to R. All right? And my H is the set of all polynomials of all possible degrees. All right? In fact, in this case, it's enough to just take degree equal to 3. Now, this is rich enough in some particular sense because polynomials can approximate any smooth function. But now the problem is, given these 3 points, there will exist infinitely many polynomials that pass through these 3 possible points. All right? Which one do we choose? There's no one choice. All of them will perform excellently on your data set. But in the end, we want to perform well on something unseen. All right? So the choice of, if H is too rich or too complex, then there's this problem of overfitting. That is, so you do very well on the training set, but do badly in the real world. All right? So therefore, we need some way of saying what does it mean to do well or do badly. Right? I've not really defined that yet. Correct? So far we've seen what it means to predict, but what is a good predictor? So in general, we are going to have a particular H, let's say from X to Y. We need some measure of how far is H of X from the actual Y. All right? So we'll define a loss function So we'll define a loss function which is from y cross y to R, but maybe we'll just restrict ourselves to non-negative reals. Okay, so this is our loss function. And the goal is to design a learning algorithm that achieves a small value of loss. Okay? Now the loss is a random variable. So we'll say that the expectation of L of y comma h of x is small. Where this expectation is taken with respect to the data generating distribution Pxy. I'm sorry?
So you define the loss
Correct.
with y cross y maps y cross.
Correct. So this is the, so one of these is going to be the actual value of y. The other is going to be the predicted value of y. So I want to know how far is the predicted value from the actual value. Okay?
So in practice,
Yeah.
can we know about the data generation model is coming from model 1 or model 2?
In general, you don't.
We don't.
You don't.
So the best thing is to assume it is coming from model
Typically, you assume that it's in model 2, but generally, model 1 is used to prove sort of lower bounds. Because if you can't do well in model 1, then it's impossible to do well in model 2.
lower bound with respect to creating a model.
We'll see. So when I want to prove an impossibility result, I'll prove that it's impossible to do well in model 1, which means that it is impossible to do well in model 2. But when I actually want to say that I can do something, when I want to prove an achievability result, I will do that in model 2, which means that I can also do well in model 1. Okay. Okay. So therefore, the goal is to design a learning algorithm that will work well on a completely independent sample. So you design, remember that the learning algorithm takes the data set as input, but I want this to be small for a completely new sample drawn according to the same distribution Pxy, but this new sample is drawn independently from the training set. Okay, so this is going to be our measure of performance. But there's a slight problem with this because, okay, I would want expected value of L of y comma h of x to be small, but this again depends on Pxy, which is unknown. All right. So then how do you really say whether the learning algorithm that you've developed is good or bad? All right. So one way to empirically verify right. So this is what I'll denote this by R of h, which is what I call the risk corresponding to h. Right, so one way is use a separate test set. Right, that's what you do in practice. You take your entire data, you split it into a training set and a test set. You design your learning algorithm based on the training set, and you verify the performance on the test set. So typically, the output that you get from the test set is supposed to be an approximation to the actual risk. All right. So then your R of h is approximately equal to 1 by m I equal to 1 to m L of yi h of xi. All right, so where these xi, yi's are drawn from the test set. But again, the assumption is that they come from the same distribution. All right. This also should tell you something about what you should be careful about, which is that the test set is sacred. Your learning algorithm should not in any way be influenced by the test set. So what you cannot do is you train, test it, and because the test results were not good, you go back to changing, let's say, the hyperparameters or changing some parameters and so on. Because as soon as you do that, you corrupted your final results. All right. The testing, so this process of learning should always go in one way. You use the training set and then do whatever you want, get a final predictor, and then the predictor should be evaluated on the test set, but you should never go back. It's a one-way process. All right, so this is what is done empirically or in practice, but we are going to use a completely different approach. What we want to do is try to develop techniques which will allow us to say whether a particular learning algorithm is good or not, irrespective, without even knowing Pxy. We'll see why that is possible and when that is possible. Okay. So just another point is that R of h is called the risk, but it's also given another name. It is the generalization error. Right, so you'll use these two terms interchangeably. Now the choice of the loss function again depends on the problem that you have at hand, but again we'll assume that this loss function is also fixed beforehand. Okay. So in the case of binary classification, one common choice is the 0-1 loss, which is L of y hat is equal to 0 if y is not equal to y hat. It's equal to, if y is equal to y hat and is equal to 1 if y is not equal to y hat. So this is a commonly used loss for classification problems, binary or otherwise. This is also equal to, I'll use the following indicator function representation, indicator y hat not equal to y. I can also consider a whole host of other losses like the squared error loss. Y hat is y minus y hat squared. All right. Or maybe an LP loss. Y hat is, let's say, the LP norm between of y minus y hat and so on. Right? So whenever we're talking about classification, we'll exclusively deal with the 0-1 loss, but in a more general setting, we'll make no such assumption. It could be any loss function.
Classification specifically to binary.
Binary or otherwise.
So what are the possible loss functions for multiple classification?
Again, 0-1 loss is the most common. Right? If the prediction is exactly equal to what is the ground truth, then it's 0. If it's anything different, then it's 1. But in general, you could also say that, let's say, if two symbols are kind of close to each other, then the loss should be smaller. But then if they are very distinct, then you want them to be different.
So, is there any metric that can estimate how well our loss function captures the difference between the predictions?
We'll assume that that is given. So that's part of the design of the problem itself.
But in general, in
you can't really say that. All right? But in general, in practice, however, loss functions are chosen based on a number of other factors, not just how well the difference between the predicted value and the actual value is. It could also depend on things like you may want the loss function to be sufficiently smooth or has some other nice functional properties. All right.
How those, what's the influence of why those two different?
Because it ultimately depends on whether you can design an efficient learning algorithm or not. So, for example, when we talk about binary classification or classification problems in general, we'll analyze the 0-1 loss. But in practice, no one almost ever uses the 0-1 loss. You always use something like a cross entropy loss or something else because they're smooth. So you want, when you design learning algorithms in practice, you want your loss functions to have additional features like whatever smoothness or convexity and so on. But from a statistical learning perspective, this is what we demand. All right. However, what should be kept in mind is that in practical machine learning problems, the loss function that is used for training or designing the learning algorithm could be different from the actual loss function based on which you're going to evaluate your output. Because in classification, typically you design the training algorithm based on the cross entropy loss or some such smooth loss function. But finally, when you evaluate your results, you still use the 0-1 loss. You find the probability that the predicted output is different from the actual output. Right. But for us, there's only one loss function for a particular problem. All right. Any other questions? I'm sorry?
Matrix, like you as you said, accuracy or precision or recall, I can't take it as a loss function in some sense.
Why not?
Means it can be taken as asking like for classification, ideally we use binary classification.
You could take any other loss function. But as I said, in this particular course, when we are trying to analyze, we will exclusively focus on the 0-1 loss. All right. But many of the results that we'll derive will hold true for any loss function. But one thing to keep in mind is that we're fixing a loss function beforehand. Right? When we're specifying the learning problem, where we are specifying, so generally we fix the domain, the label set, we will fix the loss function. This is going to be fixed throughout. And when we are talking about designing a learning algorithm, the hypothesis class will also be fixed. Right? So given this, we want to evaluate the performance of a learning algorithm. But now, so this is what we fixed. So the learning algorithm takes the data set as input. All right. Sometimes I'll use S subscript n to sort of denote that the training set has n samples. So this takes Sn as input and outputs some hypothesis from the hypothesis class H. All right. And I want to know whether this learning algorithm achieves a small enough loss or not. Okay. I want this, let's say, to be less than some epsilon. Do you notice something missing here?
With what confidence?
Okay, and why do I need some confidence?
Loss should be more the loss.
Loss is fixed, or it could be, let's assume that it's a 0-1 loss if you want.
Like means anything can be less than this one, but how much
Why do you need that assurance?
Otherwise, why should we trust that algorithm?
Okay, so let me pose my question in a slightly different way. Suppose I design a learning algorithm, okay? Again, let's assume that we're operating the agnostic setting where pxy could be arbitrary, okay? For every pxy, I want my learning algorithm to give a certain guarantee. And the guarantee that I want is that the expected value of the loss function should be less than epsilon. Do you think it is possible to achieve this all the time? Again, I'm using all the time in a very specific way. Yeah?
Does that need not represent the actual distribution?
It depends on
Correct.
the number of samples.
It's not the number of samples, it's really because ultimately what does h depend on? Little h.
Algorithm,
Data.
the data, S and
It depends on the data set, right? S. All right? It's possible that because S is now a random sample, right? And S may or may not actually capture the true distribution, because with some small probability it could be way different from what the actual distribution is. Right? So H is a random variable because S is a random variable. The output H is also going to be a random variable that depends on the sample, the training set S. So in general, I cannot expect to get a small expected loss all the time, because H is now, because there's this, what you should keep in mind is that this expectation is over a new sample. Pxy or x comma y sampled according to Pxy and independent of S, right? But now this quantity expected value L of y comma h of x is not deterministic, it's still random because h is random and depends on S. Alright, so this loss itself is still random. So what I can hope to achieve, and this is what I will demand, is that the probability where this probability is taken over S IID Pxy, I will want this to be, let's say, at least 1 minus delta, right, for some delta between 0 and 1. So if I can guarantee this, then I'm happy. If I can guarantee this for every epsilon greater than 0 and delta greater than 0, then I'm happy. All right. So this is what is called the PAC learning framework. Probably, approximately correct. Right, because this says that I'm approximately correct, and this says that I'm probably approximately correct. So this particular framework was proposed by Wazirani in '84. And then was developed subsequently. But one thing to keep in mind is that I want this to happen for every Pxy. The expectation is over the joint distribution. The probability outside is also over the joint distribution. The inner probability is over the test sample. The inner expectation is over the test sample, which is independent of the training set. The outer probability is over the probability over the training set, which are n IID samples drawn according to PXY.
Are you using the training set and test sets are coming from the same distribution?
Yes, that's a fundamental assumption.
So like why after expectation, why there will be still randomness? Means I'm not getting that. Like if I have some random variable, I take an expectation of that.
Correct?
Just give a constant quantity.
Correct, but this expectation is only taken over this y and this particular x, right? But then the additional source of randomness is in the choice of h, which is coming from the training set.
And training set again is a distribution of x.
It's again a random sample, right? Because for one training set, like let's say you design a learning algorithm. Let's say you use gradient descent to train a neural network classifier. Now this process is fixed. Given the training set, it's always the same training set. Let's assume that it always outputs the same training, the same classifier. But now if I choose a different training set, I get a different classifier. These two classifiers can perform differently, but the learning algorithm is still the same. It is, you're using gradient descent used with some particular loss function. Right? Any other questions? Okay, so if not, which is a good point to stop.